Everybody, welcome to the second video series on the gas law. So we're going to be covering Gay-Lussac's law, the ideal gas law, and the combined gas law. And this video is just about Gay-Lussac's law. So I already talked a little bit about Joseph Gay-Lussac in the last video about Avogadro's law. So I'm not going to reiterate all of that, but just remember, hot air balloons, pressure, temperature, volume is all related. And that's how he kind of recognized and discovered this law. So Gay-Lussac's law states that pressure is proportional to temperature at constant volume and amount. So we see that represented, just as like proportion on the left and as an actual equation on the right. So you want to maybe, if you want to write down that equation for your notes, be great. And let's run through a practice problem. So a scientist has some methane gas in a piston, which he keeps at a constant volume and does not add any more gas to. Normally, he keeps the gas at 0 degrees Celsius and 1520 millimeters mercury. But there's a malfunction and the piston heats up to 25 degrees Celsius. What's going to happen to the pressure of the gas? Okay, so what does this all mean? This is packed with a lot of information. So just for reference, this is what a piston looks like, and you'll see a lot of gas and ideal gas problems, like working with this idea of a piston. It's kind of like just a container, but you can, shrink the space where the gas is staying, or you can expand it. And it's normally made out of like very thick metal, so it's not gonna like expand, and that's why it's good for like controlled experiments. But I'll talk about a little bit about it on the next slide. Okay, so anyways, we know that it's in a piston, and it's, oh, sorry. It's cool that we have methane gas, but not super relevant to the problem, so we can ignore that. Just as we can just assume that it acts ideally. So he's keeping it at a constant volume, and he doesn't add any more gas to it, which means it's also at a constant amount, which fulfills the requirements to use Gay-Lussac's law. Oh, sorry, I didn't mean to X through that. Okay, and these are our base conditions, right? 0 degrees Celsius, and what are those units? Okay, so these are millimeters mercury. So millimeters mercury is another form of pressure measurement, which you're going to encounter often, maybe second most often after ATM, at least in America and on Pearson, if you guys are still using that by the time you're watching this. But 760 millimeters mercury is equal to 1 ATM, and I'll go more into that on the next slide again. But anyways, let's just set up the equation. So let's remember that P1 over T1 is equal to P2 over T2. So what's our initial pressure? Well, 1520 millimeters mercury, that's 760 times 2. So we know that our initial pressure was 2 ATM. And our initial temperature, 0 degrees, oh, not 0 degrees Celsius. Remember to convert to Kelvin. And Kelvin, of course, you would just add 273.15 to your number of degrees Celsius. So we'll have 273.15 Kelvin. And this is equal to the final pressure over 25 plus 273.15, which is 200 and, wait, I don't trust my arithmetic. 298.15. Okay. So just again, I'm going to say this in all the videos, but just make sure you're keeping track of your units. Very important, especially for our next video on the ideal gas law. Okay, so now you can just pull out your calculator and do some calculations. So 2 divided by 273.15. Oh, and let me just correct one thing real quick. This should actually say 2.00 ATM. And why is that? Well, in our expression for millimeters mercury, we have 3 sig figs, right? Because non-decimal zeros are not important. So we just have those 3 sig figs. So we should also have 3 sig figs when we convert to ATM. Okay, so 2 divided by 273.15 times 298.15. So our P2 is going to be approximately 2.183049, yada, yada, yada. But all you need to say is that P2 is equal to 2.18 because 2.18 ATM because we round to 3 sig figs. Okay. And let me just erase the rest of this before, or maybe it's not going to want to erase. Let me see. Delete. Bear with me. Okay, there we go. Okay, so lead and pistons, I said I was going to talk about this on the next slide, but this is, you might have seen this in your textbook already if you've been kind of reading along with the textbook with these videos, although you don't need to. This is a mercury barometer. So mercury, liquid mercury, it's very heavy, right? But if you put it in this, if you put it in a container like this and you have a vacuum, the pressure from the air, because air is a gas in itself, is going to basically push it down, which pushes this up. And we can measure the, millimeters of mercury that it increases by when we have that pressure. So at atmospheric pressure, 1 atm, we have 760 millimeters mercury, which is how we got our previous relationship from the last slide. And this is a piston. This is actually supposed to be a GIF, so I guess it's not super helpful just as a thing, but just imagine just as a picture, but just imagine that top top thing that kind of looks like a weight is able to move up and down in a sealed container. Pistons are just something that you're going to see a lot in practice problems and on the AP test. So we'll practice with them when we do our review of this video unit and the past video unit, which is upcoming in a few videos. I hope this is helpful, and I'll see you next time.